Unit 16, Acid-Base Equilibria, pages 227 to 239. This is about acid-base behavior. So here we're going to look more closely at what exactly is the behavior that causes something to be acidic. A polar bond in this direction creates a hydrogen atom with a partial positive charge. This tends to make the compound more acidic because the hydrogen atom is similar to the proton it will become after the acid dissociates. So basically, because this has partially created the positive charge, then it's already almost to the point where it's a hydrogen plus ion. Sodium hydride won't generate an H plus ion because the hydrogen is not positively charged. NaH is not an acid, actually it's a base. So in this diagram, you're showing that the electronegativity of hydrogen is higher, so the electrons are being pulled toward the hydrogen, which gives it a partial negative charge. And so since this does not give us even close to a hydrogen positive proton, then this is not going to be considered acidic, it's going to be considered basic. The HX bond cannot be too strong, for example in hydrofluoric acid, because when hydrofluoric acid breaks apart, the hydrogen and the fluorine are going to recombine because this fluorine is so highly electronegative that it's just going to reform the hydrogen fluoride ion or the hydrofluoric acid. And so this reverse reaction is more dominant. So because the bond between these two is just too strong, then this does not make a very good acid. So it is a weak acid as we already understand it to be. HF is a highly polar bond and polarized in the right direction, but HF is a weak acid because the HF bond is very strong and costs too much energy to break. As a result, the HF does not dissociate much and is a weak acid. So stability of the conjugate base. More stable the conjugate base, the stronger is the acid that made it. Examples of the molecular structure of acids. The CH4 molecule is not an acid because the CH bond is not very polar. So here, because these have very similar electronegativities, there is no polarity or not enough polarity for the hydrogen to get a partial positive charge, and so it's not going to be considered an acid. HCl is a very strong acid. The bond is highly polar and in the right direction, meaning the polarity is moving towards the chlorine, giving you a partial positive charge on the hydrogen. The conjugate base, chloride, is very stable, so it does not react as a base in water to remake hydrochloric acid. The hydrogen chloride bond is not too strong. So when you put hydrochloric acid in water and you get H plus and Cl minus, this ion is stable enough to remain on its own and does not try to recombine with the hydrogen to go back to the original molecule. Sodium hydride is basic because the polar bond pulls electrons toward the metal. So here's sodium hydride. It should be a dipole going this way because the sodium becomes positive and the hydrogen becomes partial negative. So upon this dissociating, you get sodium positive and hydride. And when you place this in water, you're going to get hydrogen gas and hydroxide. And it's the production of this hydroxide that makes this a base. All right, let's look at an example. Which compound is the strongest acid? And so we have HF, you'd have HCl, you have HBr, and you have HI. So notice that we said that this would have the strongest bond. So the bond gets stronger as we go this direction, stronger bond. And that's because fluorine is the highest electronegativity, followed by chlorine, followed by bromine, and this is the least electronegative, iodine, of the halogen family. So the strength of acid increases as we go down the group, so increasing acidity. Basically, because the iodine has such a large radius, it's actually very easy to remove this hydrogen and end up with H plus and I minus. So because this will separate more easily than the other three, then it's considered a stronger acid because you're going to generate hydrogen ions far more quickly than you will these other two. So the stronger the bond due to electronegativity, the weaker the acidity it is. And so you know that this is a weak acid just from general knowledge. And these are strong, and so just need to understand that they get stronger as you go down the family. When hydrogen is attached to different atoms, compare bond strength to determine which acid is the strongest. The stronger the bond, the weaker the acid. Oxyacids are acids that contain an oxygen. So you have a hydrogen hooked to an oxygen, which is also hooked to maybe a carbon compound or maybe some other things. So electron withdrawing groups are atoms with high electronegative pull electrons from the surrounding atoms. These are called electron withdrawing groups. The atoms fluorine, oxygen, nitrogen, and chlorine have high electronegativities. So each time you have one of those present on the outside of this, they are withdrawing electrons toward them in the compound. And more importantly, they are withdrawing them away from the hydrogen, creating a more positive hydrogen, allowing that to increase in acidity. So a more electron withdrawing Y group creates a more positive hydrogen atom, and this increases the strength of the acid. So here I have the hydrogen hooked to an oxygen, and there is one electron withdrawing group. And so you have a partial positive on your hydrogen there. Well, this hydrogen has two electron withdrawing groups, so it's even more partially positive than this one is. And then this has three electron withdrawing groups, which begins to make it even more partially positive. And then this one has four electron withdrawing groups, which makes this hydrogen even more partially positive. And so by the time these are ready to separate off of the compound, this is going to be closer to being independently positive compared to the others. And so this is going to be the stronger acid because there are more electron withdrawing groups pulling the electrons from the hydrogen to leave it with a stronger positive charge. When hydrogen is attached to the same atom, use electronegativities to find the most positive hydrogen atom. The most positive hydrogen atom will be the strongest acid. Example 16.76. Which of these compounds is the strongest acid? So first, let me organize them based on the halogens within them. So you have HClO, HBrO, and HIO. What's more important is to recognize that each of these are oxyacids because they have this oxygen present. So because they are oxyacids, we want to focus on electron withdrawing groups. And so what that means is the more electronegative, the stronger the withdrawing strength. And so what I'm looking at here is when I go from iodine to bromine to chlorine, this has a higher electronegativity, which means that it's going to have a stronger withdrawing ability, which is going to make this hydrogen much more partially positive than this one down here. And so the strength of the acid is going to increase going upward. And so this one is going to be the strongest, followed by this one, and followed by this one. Carboxylic acids. Remember, carboxylic acids have what's called a carbonyl group, which is a carbon double bonded to oxygen, and then an OH group here. And so here, these hydrogens are not considered acidic. However, this one is because it's attached to, or it has bond polarity that is moving towards the oxygen. Whereas remember, this bond is nonpolar, so these hydrogens are not partially charged at all. As in the case of oxyacids just discussed, addition of electron withdrawing groups increases acidity. The carbonyl group contains an electronegative oxygen atom that pulls electrons toward it, making the hydrogen atom more positive and thereby more acidic. So this is just basically showing you that this also counts as an electron withdrawing group, pulling electrons away from this hydrogen, causing it to have a strongly partial positive charge. Example 16.67. Which base is stronger? And consider that these are conjugate bases. So what we want to analyze is what was the original acid that they were. So we can figure that out by adding a hydrogen in front. And so I'll place them in order based on the periodic table of chlorine and bromine. Okay, so now I want to look at the acid strength. And remember, these are oxyacids. And so because they are oxyacids, I want to look at electronegativity. And the electronegativity is stronger as I go this way, which means that the electron withdrawing strength is stronger for this acid, making this a stronger partial positive as compared to this one. So this, between the two, is the stronger acid, and this is the weaker acid. Again, just a comparison of these two. So if this is the stronger acid, then the conjugate base is a weaker conjugate base. And if this is the weaker acid, then its conjugate base is the stronger conjugate base of these two. And so by comparison, this is going to be the stronger base between these two anions. Example 16.78, which base is stronger? So again, we want to look at their conjugate acids. So we have HBRO, which has the conjugate base BRO negative, and then we have bromous acid, which has bromite as its conjugate base. So if I want to compare the acids to each other, they're both oxyacids. Notice this one has more electron withdrawing groups. And so that means that this is going to have a much stronger partial positive by comparison to this one. So that makes this one the stronger acid and this the weaker acid by comparison between the two of them. So if this is the strong acid, this is the weaker conjugate base. And if this is the weak acid, this is the stronger conjugate base. And so this one would be the stronger base between the two of these. A Lewis acid is defined as an electron pair acceptor. So the Bronsted acid is a proton donor, but an electron pair acceptor by the Lewis definition. A Bronsted base is an electron acceptor, but a Lewis base is a Bronsted base is a proton acceptor, but a Lewis base is an electron pair donor. Determining Lewis acids and bases. This figure shows an example of a Lewis acid-base pair. How do we determine which species is an acid and which is a base? To answer this, we look at the Lewis dot structures and find what species donates and what species accepts an electron pair. So here's some clues for you. This one here, because it has a lone pair of electron, is going to be the Lewis base because it has to be electron rich, has to be able to donate electrons. Notice this one doesn't have a lone pair, so the likelihood is it's the Lewis acid. And so what we can see by the Lewis structures is that the lone pair will be donated from this nitrogen and accepted by this boron to make this complex. Notice how they get connected. So this is a Lewis acid-base reaction here. So, and this kind of shows you a little bit more detail where there's the electrons on the nitrogen and they're going to hook up with the boron to make this bond here between them. So all Bronsted-Lowry acids are going to also be Lewis acids. All Bronsted-Lowry bases are also Lewis bases. But the Lewis acid-base definition includes many more possibilities. The example above is not an acid-base reaction according to the Bronsted-Lowry definition because no proton is donated or accepted. However, according to the Lewis definition, the reaction is an acid-base reaction. Example 16.79, identify the Lewis acid and base in this reaction here. So I'm going to draw the Lewis structure for carbon dioxide is C double bonded to 2 oxygens, and water is, of course, oxygen with 2 lone pairs and the 2 hydrogens. So we have 2 lone pairs on the water. That means that it would be a good electron pair donor, and that is by definition a Lewis base. And because this has no lone pairs of electrons on the central atom, then it would be a good electron pair acceptor because it is electron deficient. And what actually happens is these electrons in the double bond actually shift up onto the oxygen, and that will create a set of 8 electrons still around the oxygen, but then that allows this carbon to accept another pair of electrons and hooking up with the pair with the water. And so then you end up with carbon double bonded to an oxygen and then single bonded to an oxygen and then bonded to this oxygen, which is bonded to 2 hydrogens, the 1 pair of electrons up here. And so you get this complex right here, CH2O3. Atoms with double and triple bonds make good Lewis acids because they are electron deficient and can readily accept an electron pair. So some examples of Lewis bases. Lewis bases must have a pair of electrons that can be donated. Here are some examples of substances that could act as a Lewis base. So we have the lone pair here, 3 lone pairs here, 2 there, 1 there, and 2 there. And so each of these are electron rich, and they can donate a pair of electrons and be deemed a Lewis base. Substances that cannot be Lewis bases, these materials do not have electron pairs that can be donated to make them a Lewis base. So no lone pairs, positive charge, no lone pairs, positive charge, and so these would not make good Lewis bases. Lewis acids. These examples of Lewis acid-base reactions illustrate some of the ways that compounds can accept an electron pair to act as a Lewis acid. So first, many cations can act as Lewis acids. Li plus has an empty valence shell that can accept an electron pair from an oxygen atom in water. And so this lithium is a Lewis acid, and this water would be a Lewis base, and then they would form this complex. The electrons in the double bond on sulfur move on to an oxygen atom. This leaves a sulfur atom with only 6 electrons, so the sulfur atom can act as a Lewis acid by accepting an electron pair from the oxygen atom in water. So because we move the electrons up here, now the sulfur is capable of accepting the pair of electrons from the oxygen. So when you see double and triple bonds, then you are likely looking at a Lewis acid. The I atom can violate the octet. In this example, the iodine atom is a Lewis atom as it accepts a Lewis acid, as it accepts an extra electron pair, 2 electrons to create 10 electrons on the central atom. So this iodine has 2, 4, 6, 8. However, because it can violate the octet rule, it can receive another pair of electrons from this iodide, making this a Lewis acid and this a Lewis base, and then you form a complex where the iodine exceeds the octet rule in the center. Here, the beryllium atom in BeCl2 is electron deficient since it violates the octet rule by having only 4 electrons. The beryllium atom acts as a Lewis acid by accepting an electron pair from the oxygen in water. So because this doesn't quite have its octet, it can accept electron pairs from the oxygens in water and then form this complex here. So that makes this a Lewis acid because it accepts electrons from the Lewis base, water. Here's your note card for this section. So if you're looking at a binary acid, not an oxyacid, then the stronger the bond, which is going up the periodic table, the weaker the acid. So this is a weak acid and it gets stronger as you go down. As opposed to oxyacids, where you have the hydrogen hooked to an oxygen plus a halogen, then the higher the electronegativity of the electron withdrawing group, the stronger the acid. And so because this has a higher electronegativity and it's an oxyacid, this is the strongest acid of these, as opposed to this one being the strongest acid of these. The more electron withdrawing groups, the stronger the acid. So here, because you have multiple oxygens attached, then you're going to have a stronger acid because you have more withdrawing groups pulling electrons away from the hydrogen. A Lewis acid is an electron pair acceptor. It's going to tend to not have lone pairs, and sometimes it's positively charged, and atoms with double and triple bonds will tend to be a Lewis acid. A Lewis base is an electron pair donor, and they will tend to have lone pairs and sometimes be negatively charged.